Okay, students, welcome again to Darasa online class, to a physics period. And today we are going to a topic of atomic physics, and it takes us to a subtopic of nuclear physics. I'm Cyprian Mgina, a physics teacher. And really into our today's subtopic of nuclear physics, we'll be looking on how to determine the half-life and the decaying constant of a radioactive substance. So I believe you all know about the behavior of a radioactive substance. That is a substance which is really disintegrating spontaneously. And that spontaneous disintegration is not influenced whether by a temperature or heat or whatever. Now from there we are having what we call radioactive laws. We are having two radioactive laws. Radioactive decay laws. The first one says that the spontaneous disintegration of a radioactive sample produces alpha, beta, and gamma rays. And the production of these three elements and particles really does not depend, or it is not being influenced by an external condition like temperature, heat, electric force, or a magnetic force. It just happens randomly. The second one is that the rate of disintegration of a radioactive sample is direct proportional to the sample which is just present. So what does it mean? It means that if the initial present sample of the radioactive material is bigger, then the rate of disintegration will just be bigger. If it is just very small, so even the rate of disintegration will also be small. So these are the two laws which will really guide us and take us to the derivation of the decaying constant and the half-life. Let us just start. For example, we are having a sample in a container of radioactive material or atoms. Then we could just be able to say that whenever at a time t is equal to 0, the number of sample we are having in my container, let me take to be equal to n naught. So initially at t is equal to 0, the sample I'm having in my container is n naught. And as time goes on, there is a disintegration which proceeds. And this disintegration, whenever it proceeds, the sample in my container will be decreasing. So there will be a decrease of the radioactive sample with time, such that at time t, at a time whenever is equal to t, let us say that the sample we have just remained in my container to be equal to that much. So we could now just be able to look from the second law that the rate of disintegration, that is the n dt, that is the n dt. This we are saying that is always proportional to the number of samples, that we are having at any particular time, t. And if we are removing the proportionality sign there, then we could just be able to have the n dt will just be equal to minus lambda times n. And the proportionality sign lambda here is what we call the decaying constant. So the lambda there, this is what we call the decaying constant. Decaying constant, and the negative sign here, it shows that the sample we are having continues to disintegrate. It decreases with time. So the negative sign is there, it shows that the radioactive sample decreases with time. So we are really having from that particular expression number 1. Now, if we're just going now to apply a calculus from this particular expression, then we could just have this particular equation. It's just a matter of rearranging that particular expression. Let's just take nt dn over n, then this will just be equal to minus lambda dt. So having obtained this particular expression, we can just be able to integrate both sides. If we integrate both sides, the negative and lambda, that's a constant, can be taken outside, and then we'll just be having the logarithm to base e of nt. This will just be equal to minus lambda t plus a constant of integration. So we are having that particular expression whereby k there is a constant of integration, and our interest is to determine the constant of integration k. The value for k can be obtained at boundary condition. That can just be obtained when the time t is just equal to 0. We need just to determine the value for k. So when the time t is equal to 0, the initial number of atoms or of our radioactive sample we are having, the nt here actually will just be equal to n naught. N naught representing the initial number of sample of the radioactive material we are having in our container. Such that if we're just going to substitute these values to this particular expression, then we are having that at t is equal to 0, then this particular nt will be equal to the natural log of n naught, and this will just be equal to k. And hence I can be able to substitute k to this particular expression to obtain the general expression. So if I'm taking this particular expression, substituting there, then I will be having the natural log of nt to be equal to minus lambda k, lambda t, to be equal to lambda t, and plus natural log of n naught. And if I take this, and if I'm just going to take this to that particular side, then I'm just going to have the natural log of nt, of course, minus the natural log of n naught, this to be equal to minus lambda t, or in other language, I'm having nt over n naught. So the whole of this is just be equal to minus lambda t. And therefore, if we're just going to write, if I do proceed from that particular expression, then I'm just going to have nt over n naught. This will just be equal to e power minus lambda t. And therefore, the number of sample of the atoms at any particular time t, this will just be equal to n naught e power minus lambda t. So we are having this particular expression, which is very, very important in conjunction with the other first equation and the second equation we have just obtained previously. So here we are just going to get the number of sample of the radioactive atoms at any particular time t be given by that particular expression. Remember, the lambda there is what we call the decaying constant at particular time t. Okay, so we have just obtained this particular equation as equation number 3. Okay, students, then we have already seen this particular expression, which is really represents the rate of the decay of a substance in a container with time. And this decay actually is exponential, such that if we plot a graph if we're going to plot a graph, let's say, representing the number of sample present with the time t, beginning at t is equal to 0, the number of sample is equal to n naught, the initial sample. And this decay goes like this. So this decay is exponential and is really represented by that particular expression number 3 there. So now, we could just be able to see now, or we can just be able now to determine now what we to determine now the decaying constant. We could be able to determine and be able to see what will just be the definition of the decaying constant. From the previous expression, whenever we are looking the decaying constant, which is lambda, we just found that the n dt, this is just equal to minus lambda n. We had already obtained this particular expression, such that the lambda there is the decaying constant. And if I transpose and put lambda to be the subject of the formula, actually I will be having the n dt, over n. And with this particular expression, of course with the negative sign there, with this particular expression we could just be able to define the decaying constant as the rate of disintegration per unit atom which are just present in a sample. So that will just be the decaying constant. That will just be the decaying constant, which can just be given by this particular expression number 4. Just before we proceed looking the decaying constant, we could just come back again to our expression number 3. That the number of sample which are just present at time t is just equal to that much. Now, for example, let us just take at the moment the decaying constant is just equal to 1 over t. Then what does it mean? It means that the whole of this particular expression will just be reduced and be like this. That the number of sample present at time t is just equal to n naught e power minus 1, because the lambda there is just equal to 1 over t. And you could just be able to find that if I'm taking the number of sample present, this will just be equal to n naught over e. This will just be equal to n naught over e. And if I compute there, you'll just be able to find that this is just equal to n naught over e, which is equal to 2.718, and actually this will just be equal to 0.3678 n naught. So it means that the number of sample of the radioactive material which are just present will actually just be equal to 0.37 of the original sample which were there at the very beginning at t is equal to 0. So what does it mean? We could be able to have another equivalent definition of the decaying constant. That the decaying constant could just be taken or explained or defined as the reciprocal of the time at which the original sample of the radioactive material is going to fall, to decrease due to the spontaneous disintegration, is going to fall to about 37% of the original sample n naught. So that could just be an equivalent description of the decaying constant, which is lambda. Okay, so having looked at the decaying constant, let us go and look the half-life of the radioactive sample. Let's just look at the half-life of the radioactive sample. The half-life. That particular half-life can sometimes be abbreviated with the capital T, or to some other books they could just be take this as T1/2. This is the half-life of the radioactive sample. By a definition, a half-life of radioactive sample is the time taken by the radioactive sample to decay to a half of its original value. So the whole sample which were initially present, if we are N0, then the time it takes for this particular sample to be reduced to a half, to N0 to a half of that much, that particular time is what we call the half-life. And we could just be able to determine this a half-life. Let us look. From our original expression, we had said that the number of atoms at time t just be equal to that much e power minus lambda t. Now let us assume that for a half-life, the time t, let's take it to be equal to t. That is the half-life. And if that is the case, then the number of atoms present at that particular moment, the number of atoms which are present at that particular moment is going to be reduced to a half. And therefore, the whole of this particular expression, we're just going to have n0 over 2, this to be equal to n0 into e power minus lambda times t, t being the half-life of that particular radioactive sample. And therefore, you could just be able to find that that and that will cancel, that we're going to have a half to be equal to e power minus lambda t. We're having something like that. And our interest is to determine the t there. And we can really be having, e power minus lambda t, this is equal to 2, or in other language I could be able to say e power lambda t, e power lambda t, capital T, the half-life, this is equal to 2. So we can just be able to take log on both sides, natural log on both sides, so that here we'll just be having the lambda times t. If I'm taking ln to both sides, so here I'll be having the natural log of 2. And therefore we could be able to determine the half-life t to be equal to ln of 2, the ln of 2, the ln of 2 over lambda, okay, ln of 2 over lambda. And therefore we could be able to compute for the ln 2, whereby the half-life, this will be equal to 0.693 over lambda. So we are having that particular expression, which is really very, very important. So it shows that the half-life of a radioactive sample is just being equal to 0.693 over lambda. Now, having obtained this, where the lambda there is the decaying constant. So what does it mean? It means that if we are talking about a radioactive sample to be decaying, actually, if I'm going again to draw the graph, of the number of radioactive sample versus time, this particular decay is exponential according to this particular equation. And that particular exponential decay goes like this, such that if this is at t is equal to 0, if the original number present is n0, for the first half-life, that whenever the original number of atoms are going to be reduced to a half, the first half-life will be here. And if the second sample is going to be reduced to a half, it will be n0 over 4. Then the second half-life will be somewhere there. And if that particular sample is going to be reduced to a half, then the third half-life is going to be there. This will be n0 over 8. So it goes like this, that here if it is n0 over 16, then the half-life of this could go and be there. This will be the fourth half-life. So we could have various half-life just depending depending or having the number of radioactive sample to be reduced to a half at every time, so that we could just be able to determine how many half-lives that particular radioactive substances is going to suffer. So that is an equivalent expression of the half-life. So by a definition, and from whatever we have just derived, we could just be able to see that kind of a relationship between the half-life and the decaying constant, as well as graphically the decaying constant is an exponential decay, as we can be able to see here. And really, from various mathematics, we can as well be able to do and obtain whatever we could just be given or be asked in particular problems. Okay, students, now having seen this, we can now just go so straight to look to some questions which I have just prepared them for you, and these will just be some examples. But I believe after doing those examples, you will just be in a position to do even some more difficult questions. But let us try to look for those examples. I've just prepared it for you. Okay, students, to our question number 1. The question goes like this. The half-life of the radioactive element called radon is 3.8 days. Now find the percentage of the atoms which will be present after 20 days. So this question, as we can be able to see, is very short and straightforward. That the half-life for a radon is given to be 3.8 days. And therefore, we could just be able to find that from that particular, for the question number 1, we can be able to find that from that particular expression, where we have n naught into power lambda t, then find the percentage of the atoms which will be present after 20 days. Is the number of atoms which are present at time t over the original number present at the beginning. So this is just equal to e power minus lambda t. But we all know that the half-life t is just equal to this much. So if I transpose and put lambda to be the subject of the formula, so the lambda there is 0.693 over the half-life. And the half-life there is given 0.693 over the half-life there is 3.8 days. So this will just be equal to 3.8 days. So what we are going to do is just to compute now that we substitute this particular value. So if these are the days, then we need just to multiply by 60 times 60 times 24 as days. So this will just be per second. So the whole of this will just be taken to be per second, not per day. And therefore, we could just be able now to compute and substitute it over there, so that nt over n naught, this will just be equal to e power minus lambda. Now the lambda is equal to this much, and the t, that will just be the 20 days, so it will just be equal to 0.693 over 3.8 times 60 times 60 times 24, that is 3600 times 24 times t. Now the t is 20 days, so we can take 20, and again this 20 we can be able to multiply by 3600 times times 24, so that the whole of this can cancel with that one. So we're just remaining with that one, and we can be able to compute for this. And if we go using our calculator, then we could just be obtaining something like this. So we're getting e power minus 3.646473 7368, and we could just be able to look for this value, that this value is, so this value is 0.026059. Okay, and this is n the number of sample over the original number. And if we are going to look to a percentage, actually we need just to multiply to 100, because we are being asked to determine the percentage of the atoms which will be present after 20 days. And in terms of percentage, you could just be able to see that in terms of percentage, this is 2.6%. So that will just be the answer for this question number 1. The question number 2 goes like this. The radioactive sample of radium has a decaying constant of 4.28 times 10 power negative 4 per year. Determine the following: the half-life of the radium and the time after which its strength is reduced to 1/10 of its original value. That is question number 2. So we can go so straight to our formulas we have just derived and use them to do this question. So the radioactive sample of radium has a decaying constant of that much. So the decaying constant is given, which is 4.28 times 10 power negative 4. 10 power negative 4 per year. Okay, so we need to time the half-life of the radium. The half of the radium, we all know that the half-life is just be equal to 0.693 over the decaying constant. So we can be able to determine the half-life very so straight, which is 0.693 divided by 4.28 10 power negative 4. And this half-life will be in terms of years. And we can be able to compute so straight. So this half-life from my computation here will be equal to 1,619.15 for approximately 16 years. So this will be the half-life of the radium. Let's go to part B. We are being asked to determine the time after which its strength is reduced to 1/10 of its original value. Its strength is going to be reduced to 1/10 of its original value. So that here, from our expression of nt to be equal to n naught e power minus lambda t, we need to determine the time at which the strength is reduced to 1/10 of its original value. So for that particular case, we just take the strength to be 1/10 of its original value. It means that if I'm taking nt over n naught, then this will just be equal to 1/10. And therefore, we could just be able to say that 1/10 here to be equal to e power minus lambda t. That means that we are just going to have 1/10 to be equal to e power minus lambda, that is 4.28 10 power negative 4 times t, and then it means what? It means that if I'm taking e power 4.28 10 power negative 4 t, then this will just be equal to 10. Okay, it will just be equal to 10. So that if I'm taking natural log to both sides, then here I'll be having 4.28 10 power negative 4t. then this will just be equal to the natural log of 10. And we could just be able to solve this. So this will just be equal to 2.302585, okay, will be equal to this much. So the time t will be equal to this much divided by 4.28 times 10 power negative 4. And if we divide there, so we are going to get 5,379.87. This will just be years. So the time at which its strength is going to be reduced to 1/10 of its original value will be equal to this much. Okay, students, let's go to question number 3. The question goes like this. The half-life of a radioactive sample is 1500 years. Determine the time it will take for 1 gram of this radioactive sample to lose a centigram and B, to be reduced to a centigram. So this is the question number 3. We can be able to do it comfortably as by just using the formulas we have just derived here. First of all, we need to know a centigram. If I'm taking 1 gram, a centigram is 1/100 gram. And whenever we need to determine the time it will take for 1 gram of a radioactive sample to lose a centigram, so it means what? It means that the sample which is going to be left, remember we are having our equation that the sample at any particular time t is just equal to nt, which is equal to n naught e power minus lambda t. Now the sample which will be left, if I'm taking the original sample is 1 gram, that will be n naught. So the time it takes to lose a centigram, that is 1/100, the sample which will be left after that particular time t will just be equal to 99/100. So if that is the case, we could just be able to substitute the values here. That the sample left after time t will be equal to 99/100, and the original sample there is 100/100, which is 1 e power minus lambda t. And we all know that, and we all know about the decaying constant. That the decaying constant is just equal to 0.693 over the half-life. And the half-life is given, which is 1500 years. So you can be able to determine the decaying constant lambda there. So this will be equal to 0.693 over 1500 years. So this will just be per year. This will just be per year. And therefore, if we compute for that, we can be able to obtain the value for lambda. So the lambda there is 4.62 10 power negative 4 per year. That is the value for the lambda. Now we come back here that whenever I'm looking the ratio of nt over the original sample, which is equal to e power minus lambda t, then here we are looking the ratio of the sample at time t with respect to the original sample there. So actually we're taking this divided by this, which actually it goes and gives us to 99. It goes and gives us to 99/100, so that this will just be equal to e power minus lambda times t. So the lambda there is 4.62 10 power negative 4 times t there. So our interest is to determine this t, and therefore we can be able to proceed computing for that, and really we'll be getting, here will be 0.99 into e power that much, 4.62 10 power negative 4 times t. So that if I compute to both sides and take the natural log, then you could just be able to see that I'll be having e power 4.62 10 power negative 4 t. So this will be equal to 1 over 0.99. And if I take if I take ln to both sides, I'll be having 4.62 10 power minus 4 t. Then I'll be taking the ln of that. The ln of this, which will be equal to 0.001, 0.01005 0335. So the value of t there, I have to divide by this much. If I divide by 4.62, so I'm getting 21.7539 years. This is part A. Let's go to part B. We are to determine the time it will take for 1 gram of this radioactive sample to lose or to be reduced to a centigram. To be reduced to a centigram. What does it mean? It means that the sample which is originally present will all be able to decay spontaneously until the sample which is left is just a centigram. That to be reduced to a centigram. So if we are going back again to our famous expression there, if we are going back again to the famous expression there, it means what? It means that the sample we are having, that the sample which we are just going to have, if the original sample is 1 gram, so the sample which will be left is just a centigram. That will just be 1 over 100 of a gram. And therefore this will just be equal to the sample at time t. While the original sample is 1 gram, this one will just be equal to n naught. And therefore we could just be able to write like this. That is 1 over 100. This will just be equal to 100 over 100, or 1 gram, e power minus lambda t. And therefore we could just be able to see that if I'm taking this over this, then it's just like 1 over 100 to be equal to e power minus lambda t. And the value for lambda is obtained, which is equal to this much, and therefore we need just to look for the time t. So 1 over 100, so you'll be having 1 over 100 to be equal to e power minus 4.62 10 power negative 4 times t. And we can proceed here computing, okay? For 1 over 100, that is 0.01. And this is equal to e times that much. E power 4.62 10 power negative 4 t. And if I cross multiply, then I will just be having e power 4.62 10 power minus 4 t. this is equal to 1 over 0.01, or which is just equal to 100. If you just take 1 divided by 0.01, is just equal to 100. And then we take ln to both sides, so that we are going to have 4.62 10 power negative 4 t, 10 power negative 4t, this to be equal to 100. We need to solve this will just be equal, if I'm taking ln to both sides, this will just be equal to ln 100. And we need now to solve for that, which is 4.60517700186. And therefore, to determine the time t, I need to take this divide by 4.6 10 power negative 4, that is a decaying constant. That is 4.62 10 power negative 4 to obtain the time t, so that we could be able to divide that particular expression, divide by 4.62 times 10 power negative 4. So this is 9,9967.9 years. So it takes 9,967.9 years. You can be able to see that sometimes you can be able to approximate about 10,000 years. So that this will be the time at which 1 gram of the radioactive sample will be reduced to a centigram. So that is question number 3. Okay, students, let's now just go, let us just go for a homework question. So the homework question goes like this. A sample of a radioactive source at an instant contains 10 power 12 atoms. Now, if the half-life of this radioactive sample is 30 days, A, calculate the number of disintegration in the first second. B, what time will elapse before 10 power 4 atoms remains? And C, what is the count rate at this time? So this is the question. We can take this as your homework, but let me just give you a hint. Remember here, we are given the sample to contain 10 power 12 atoms. So the original number of the radioactive sample present in our container to be equal to 10 power 12 atoms. Okay? And the half-life for this particular sample is 30 days. So if we are going for part A, calculate the number of disintegration in the first second. The number of disintegration in the first second. So remember, we are having our famous expression. Nt is equal to n naught e power minus lambda t. And remember, the n dt is just equal to minus lambda t. So the rate of the number of disintegration is just equal to the n dt. So what you are supposed here for you to do is to obtain the lambda, and the lambda can just be obtained. The lambda can just be obtained because it is equal to 0.693 over the half-life, and the half-life there is given, which is 30 days. So you can be able to obtain the lambda there. Obtaining the lambda there, you can be able to determine the number of disintegration in the first second. You can be able to obtain that. That is A. For part B, you need to determine what time will elapse before 10 power 4 atoms, that is 10,000 atoms remains. So there you know that the original number is just equal to this much. Then you need to determine the time that after that particular time, the number of atoms are just going to be reduced to 10 power 4. So you really need to use this particular expression, so that this number in terms of atoms will be 10 power 4, but the original number here it is 10 power 12. And therefore you can be able to calculate the NT there. That is for B. You can be able to see that is so straight. And the lastly is the count rate. Actually it comes from this particular expression. That is the n dt is equal to minus lambda n. And then you can just be able to determine this. That will be giving you the count rate. Students, having obtained all of these particular expressions, formulas, the way we have just derived to see the rate of disintegration, the decaying constant, the half-life, I believe you can just be able to embark into several questions which you could just be able to solve so comfortably. And I believe if you are given, or if you are going to meet with those particular problems, you can be able to solve those particular problems without any problem. Thank you, students, for today, and see you next time.